Very good afternoon, one and all. So myself, Dr. Shankar Mani. So today we are going to discuss about isomerism, definition, classification, and a brief note about classification. So first definition, isomerism is defined as the organic compound which is having same molecular formula. It used to differ in structure. It means it used to differ in physical and chemical properties. So in that first is types of isomerism. We are classifying that isomerism into two categories. One is structural isomerism and another one is stereoisomerism. Under structural isomerism, further it used to classify into chain isomerism, positional isomerism, functional isomerism, metamerism, and tautomerism. So what is structural isomerism? Structural isomerism is an organic compound, means it is defined as that organic compound. It used to have same molecular formula, but it used to differ in structural formula. If I am coming for stereoisomerism, it used to have same molecular formula, it used to have same structural formula, it used to differ only in the arrangement of atoms. It means differ in configuration. So stereoisomerism further classified into two categories. One is geometrical isomerism and another is optical isomerism. First, we will start with structural isomerism. Structural isomerism, already I told the definition, compound have the same molecular formula but differ in structural formula. So first, if I am going for chain isomerism, it used to have different arrangement of carbon skeletons. It won't contain such type of compound. It won't contain any which one functional group. It is made up of carbon hydrogen. It used to have similar chemical properties, slightly different physical properties. But if I am seeing boiling point, it used to differ. It used to differ. But next, if you are going for positional isomerism, the compound used to have same carbon skeleton, same functional group. That functional group is in different position. So it used to similar chemical properties, but it used to differ in physical properties. Then if we are going for which one, functional isomerisms or functional isomerism, it used to differ in functional groups. I can give example. If I am taking dimethyl ether with which one, ethyl alcohol, it is having the same molecular formula, but if I am seeing structure, it used to get different. It is having different functional groups and different chemical properties and different physical properties. Next, if you are discussing about which one, metamerism. So metamerism is a type of organic compound. It used to have equal group of which one, equal group of molecule. It used to present in both sides of a functional group. Example, I can tell dimethyl ether or diethyl ether. So such type of compound we can read it in which one, metamerism. So tautomerism, we are discussing about which one, keto and enol forms. Keto enol forms. So keto enol form, in the sense all keto compound, it is not stable. It may take one hydrogen from neighboring carbon. It used to convert it into unsaturated enol form. So both are not stable. If it is in the form of enol, it used to convert it to keto. If it is keto form, it used to convert it to enol. So next, so some examples for each and every chain isomerism, structural isomerism I given here. For example, if you are going for which one, butane, N-butane, and which one, isobutane, N-butane, isobutane, both are having the molecular formula C4H10. But if you are seeing the arrangement of which one, carbons, in butane it is straight chain, but in which one, isobutane, it used to present in branched chain. Once, if I am going for which one, giving chemical name, so that isobutane we used to call it as 2-methyl propane also, 2-methyl propane. So here if I am seeing, it is having different carbon skeleton, similar chemical properties, slightly different physical properties, but if you are seeing boiling point, it used to get low. Next, structural isomerism, the same structural isomerism. We can take that same examples, straight chain and branched chain, straight chain and branched chain. In structural isomerism, chain isomerism, we saw. So next we are going for which one? Positional isomerism. In structural isomerism, positional isomerism. So in positional isomerism, I can speak about which one? Position of functional group. I can speak about double bond, which is present in a carbons. So here I give an example as which one? Position of double bond in alkenes. Double bond in alkenes. Commonly, if I am seeing, so here it is having 5 carbon. Commonly, if double bond is present in any carbon, generally we used to call it as which one? Pentane. Pentane. But in this positional isomerism, we can identify the double bond where it is present. That we can see. So next one is which one? Positional isomerism for aromatic compound. Aromatic compound. So if it is not having functional group, we used to mention that position as ortho, para, meta. Suppose if it is having functional group, we used to give numbering like 1, 2, 3, 4. So here all structure it is having 2 chloro groups only, but the position of chloro group is different. In first structure it is present in 1 and 2, in second structure 1 and 3, and in third structure 1 and 4. 1 and 4. Next, functional group, structural isomerism with functional groups. I discussed already. If I am comparing alcohol with ethers, alcohol with ether, ethyl alcohol with dimethyl ether. If I am saying molecular formula, it used to have same, but functional group is different, chemical properties is different, physical properties is different. Same I can take aldehyde and ketones, aldehyde and ketone, many aldehyde and ketones. So for example, here I taken which one? Propanaldehyde and propanone. If you are saying molecular formula, both are same, but structure wise, physical property wise, chemical properties wise, it is different. Next, acids and esters. Acids and esters. Any acid esters related number of carbon. If number of carbon is same, such type of compound, if you are taking, it used to have different functional groups, different chemical properties, and different physical properties. So next, we are going for which one? Stereoisomerism. Stereoisomerism. So stereoisomerism, the definition we saw that molecule having the same molecular formula, but that atoms are joined each other in different spatial arrangement. Or we can call it as that compound, it used to have same molecular formula, same structural formula. It used to differ only in configuration. So we are classifying that stereoisomerism into two: geometrical isomerism and optical isomerism. So now we can go for the introduction of which one? Geometrical isomerism. Geometrical isomerism. So geometrical isomerism, further it used to classify into cis and trans. Cis and trans. So cis, what it is trans. So this all geometrical isomerism is applicable only for alkenes. Alkenes, that compound which is having double bond. If it is saturated, we can't read geometrical isomerism. We can't read geometrical isomerism. Next, if you are going for example, so here I given which one? Butene, cis-butene and trans-butene, how we are telling. So here that group or atoms are on the same side of the double bond, same side of the double bond. You just see the structure. So in cis isomerism, 2H in different carbon is present in same side, and a 2-methyl group which is present in different carbon is present in opposite side. So if same group of molecule or an atom is present in same side of different carbon, that we used to call it as cis. If it is present in opposite side, we used to call it as trans. So here, if I am taking cis and trans, it used to have different physical properties, boiling point, density, but sometimes it may have same chemical properties, same chemical properties. So if the compound is having double bond, it used to restrict the rotation. So that's why we are reading this geometrical isomerism in two forms. One is cis and another one is trans. So next, what are the which one different compound, how we can read? Okay, which one is correct, which one is same? So I told already that the same atom or a molecule of different carbon or double bonded carbon, if it is present in same side, then it is call it as either cis, or if it is an opposite side, we are calling it as trans. Suppose in a same carbon, same atom is present, you just see that second structure. So in the second structure, in a carbon, one carbon is having 2 methyl group, one carbon is having 2 hydrogen group. Such type of compound is not a geometrical isomerism, So here in this geometrical isomerism, if the compound is made up of carbon hydrogen with a double bond, we can express it as cis or trans in geometrical isomerism. Suppose if organic compound with unsaturated double bond with different functional groups, we used to mention it as which one? ENZ. So that is called it as indigent or Susaman. So next, optical isomerism. So any organic compound, if it is having non-superimposable of mirror image, then we can call that compound is optically active. So isomers. Here, before going for optical isomerism, we have to know about what is enantiomer, what is diastereomer, what is which one chiral center, etc. So enantiomer means if any organic compound is having non-superimposable of mirror image, if it is horizontal or vertical, then we can call that compound as which one? Enantiomer. If compound is enantiomer, that compound is optically active. Suppose if one carbon is surrounded by 4 different functional group or atom, then we can call that carbon as chiral center. Chiral center. If organic compound is having chiral center, then compound is automatically optically active. But not all compounds. Best example, meso compound like tartaric acid, it is not having, even though if it is having chiral center, we are not considering it as which one optically active compound. Why? Because half of the structure is the mirror image of next half of the structure. But by changing the configuration, we can convert that meso compound into optically active compounds. Next, if chiral center contain a carbon, we can call it as which one? Asymmetric carbon atom. So other name of chiral carbon is asymmetric carbons. Asymmetric carbons. So here in chiral carbons, so we are having n number. So see here, first structure 1 chlorobutane is not having any chiral carbon. 2 chlorobutane is also not having any chiral carbons. In that, if carbon is surrounded by 3 different functional groups. So for example, you take 3 chloro. Okay, so that is 2 chlorobutane. 2 chlorobutane in that third carbon is not third carbon, second carbon is a chiral carbon. Why? Because in a second carbon, one side it is having hydrogen, one side it is having chloride, one side it is having methyl group, and one side it is having CH2. So among these four structure, only 2 chlorobutane is an which one? Chiral carbon or chiral center containing carbons. So now we studied optical isomerism means non-superimposable of mirror image. If we are showing any structure, if it is opposite to the structure in a mirror, that we are calling it as non-superimposable of mirror image. Maximum all organic compounds, it is non-superimposable of mirror image. We can't tell all, some organic compound is having superimposable of mirror image also. Then we are coming for optical isomerisms. So superimposable, non-superimposable we studied. So best example we can take which one? Chiral center containing compound. So example is which one? Lactic acid. Lactic acid is having one OH, one hydrogen, one CH3, one COOH. So if you're showing that structure in front of mirror, it used to show oppositely. Based on that, we are classifying that optical isomerism into two categories. One is called it as D form and another one is L form. Suppose in a polarimeter, polarimeter is a type of instrument to identify that compound is optically active or not. So if that plane of polarized light which is present in polarimeter, if it is rotating in clockwise, then we are telling that compound as optically active, and it used to rotate in anti-clockwise. Then the name of rotating in clockwise, we are mentioning it as which one? D form, or we can call it as which one? Plus form. In a polarized light, if compound is rotating in anti-clockwise, then we are expressing it as levorotatory, or we can call it as I or minus form. So some compound, which one without keeping in polarimeter, by seeing the structure itself, we can tell that compound is positive or plus form or minus form by calculating the molecular formula from lower atomic weight to higher molecular weight, or low molecular weight to higher molecular weight, in which manner it is getting moved. Based on that, we can tell whether it is clockwise or anti-clockwise. So all optically active compound is enantiomer. It used to have chiral carbon. It may available in the form of plus or minus. Sometimes if compound is optically active also, it may not rotate in polarimeter. Suppose if compound is racemic mixture. Racemic mixture means if the compound is having 50% of plus form and 50% of minus form, such compound we are calling it as which one? Racemic mixture. If it is a racemic mixture in a polarimeter, it won't get rotate. But by which one? Separating that racemic mixture, we can convert that racemic mixture into optically active. So with this, I am concluding this isomerism today's class. So tomorrow we will start with which one? Optical isomerism. Once again with plus form, minus form, dextrorotatory, levorotatory, or S forms. Thank you.